Hello there. In this video, I am going to discuss detailed solutions of all the questions those are appeared in GATE 2010 pertaining to the subject communications. These are the question numbers you will find in GATE 2010 paper which are from communication subject. I will discuss solution detail one by one. First question is question number 20. Suppose that the modulating signal is mt equal to 2 cos 2 pi fmt and the carrier signal is xct which is equal to ac cos 2 pi fct. Which one of the following is a conventional AM signal without overmodulation? We have to check each and every options. So what is basically the conventional AM modulation? Conventional AM modulation is nothing but is the AM signal which is DSB plus C, that is double sideband with carrier, which we can represent mathematically as shown in this expression, that is AC whole into 1 plus MT divided by AC, because AC is taken outside, so 1 by AC will be here, and there will be the carrier, that is cos 2 pi FCT. This is the standard form of conventional AM signal. Now let us check each and every option. The first one is simply DSB with suppressed carrier, because there is no plus AC cos 2 pi FCT. Here if you see, if you expand this, the AC cos 2 pi FCT is there as a separate term, but here there is no AC cos 2 pi FCT, that is the carrier is suppressed in this case. That is why this is called DSB AC. So this is not a conventional AM modulation. Next, let's check for option D. Option D, if you see, this is nothing but the expansion of cos C minus D. Okay, because cos into cos function is there plus sin into sin function is there. So we can simply represent this as AC cos 2 pi FC minus FMT. This is nothing but FC minus FM is nothing but the single sideband, that is the lower sideband amplitude modulation. So you can say this is the SSB, that is the single sideband AM modulation. So this is also not the conventional AM signal. So option D is also eliminated. Next, if you see in option C, we can take AC common, then we will represent the signal as represented here. Here if you see, the modulation index is nothing but 1 by 4 and MT amplitude is 2. So 1 by 4 will be multiplied by 2. This is the modulation index. Next, if you see in option B, we can find out the modulation index. Modulation index will be simply, if we substitute MT, that is 2 cos 2 pi FMT here, then that 2 coefficient of cos will be the modulation index. So here the modulation index is 2, and in option C, the modulation index is, because 2 amplitude is there for cos 2 pi FMT, that will be multiplied with 1 by 4, so modulation index will become 1 by 2 here. So B and C both are representing conventional AM signal, but we have to see as per the question which one is not over modulated. If you see, if modulation index is greater than 1, then that is the case for over modulation. So in option B the case is over modulated, whereas in option C it is under modulated. So option C is the correct match as per the requirement of our question. Hence option C is the correct answer for question number 20. Next question is question number 21. In this question, consider an angle modulated signal xt which is equal to 6 cos 2 pi 10 to the power 6t, that is the carrier frequency, plus 2 sin 8000 pi t plus 4 cos 8000 pi t. The average power xt we have to find out. Basically, when the signal is in this form, that is AC cos phi t can be anything, or AC sin phi t, then the power is always equal to AC square by 2, that is the average power. Okay, so here if you see, the amplitude is 6, so simply the power will be 6 square by 2, that is 18 watt. Option B is matching with the 18 watt, so option B is the correct answer for question number 21. Next question is question number 24. In this question, Consider the pulse shape ST as shown. The impulse response ST of the filter matched to the pulse is, we have to find out which one is the impulse response among the options, that is the impulse response of the matched filter when ST is the input. So what is the match filter response when input is ST? The match filter response, that is the match filter impulse response, will be S capital T minus small t, okay, where T is the duration of the pulse, that is T, maximum T here. So we have to draw this S T minus T from this simply ST signal. How we will draw that? We can represent this, we can represent the S T minus T as this form, that is S. If you take negative outside, then it will be looking like this. That is what are the things happening here. First we have to fold this one, that is first folding about y-axis is occurring, then shifting towards positive x-axis is happening. So we will do the same chronologically. So first when we will invert this one or fold this one about the y-axis, that will give us S minus T and the waveform will be looking like this, okay. Then we will shift this waveform towards the positive x-axis by capital T seconds. So if we shift this, it will be looking like this, and this is nothing but the match filter impulse response. So if you see, we have a exact match with option C, okay. So C is the correct answer, that is the impulse response ST of the filter matched with the input ST. Next question is question number 43. In this question we have to find out for this signal what is the Nyquist sampling rate. Here if you see, basically two sampling signal or two sync functions are multiplied. We have to find out what is the Nyquist rate of this signal. So the signal ST is given 1 by pi square t square, that is pi t if we take at the denominator. Then if we multiply half, then we can represent this in summation as this, because this is A, this is B. So one will be A plus B, another will be A minus B. So we will have this expression. Here if you see, the frequency, that is the maximum frequency, is nothing but 1200 pi radian per second. So we can find out, if we divide by 2 pi, then we can get the maximum frequency to be 600 Hz. Then the Nyquist rate is nothing but 2 times of the maximum frequency. So the Nyquist rate is simply 1200 Hz, and that is what is asked in the question. So option C is matching with our desired result. Hence the Nyquist rate of this signal is 1200 Hz. Alternatively also, if we can draw the signal in frequency domain, that is by taking its Fourier transform, then we can find out what is the maximum frequency. So twice of the maximum frequency will give us the Nyquist rate of this signal. We know sampling t equal to sin t by t, and sampling pi t will be equal to sin pi t by pi t, or this is nothing but the sync function, that is sync t. Coming to our signal, in the first part, if we divide 500 here, then 500 will be multiplied at the numerator. Then the first part can be represented as 500 sampling 500 pi t, okay. In the second part also, if we multiply 700 and divide 700, we can represent, that will be 500 sampling 500 pi t into 700 sampling 700 pi t, okay. Now let us focus on the Fourier transform. When a rectangle function is there in the time domain, then what is its Fourier transform? This is the generalized formula which you can remember, so that you can find out the Fourier transform of any square wave. Here if this omega we can represent 2 pi f tau, then the same signal can be written as a tau sampling pi f tau. Now applying duality property, that is this will become in time domain and this will become in frequency domain, then we can represent this a tau sampling pi f tau as a tau sampling pi tau t, that is f becomes t here and here t will become f. Rest will remain same because the signal is even, so the same signal will be represented here, only the axis will change to frequency. So what is the duality property? Let us see the duality property. If xt has the Fourier transform x of f, then x of t, that is this capital X of t, will have a Fourier transform of x of minus f, because that is coming in frequency domain and one negative will be there. Here because this is a Wien function, so negative of f will not affect the frequency domain signal. That is the shape will be same as that of the time domain. Now let us apply this property here. By applying this property we can find out what is the Fourier transform of this, and again also we can find out the Fourier transform of this. So what will be the Fourier transform of 500 sampling 500 pi t? Here tau is simply equal to 500 because here tau is there, t is there, pi is there, so pi is there, t is there, so tau is simply 500 and this is nothing but a tau. Okay, as tau is already 500, so a is simply 1. Hence the Fourier transform will become tau by 2. Tau by 2 is nothing but 250. So the rectangle pulse will be from minus 250 to 250 and the amplitude will be simply 1. Okay. Similarly, for 700 sampling 700 pi t, the Fourier transform will be like this. That is, the duration will be from minus 350 to 350. Now the signal st has two factors that is multiplied in time domain. What will be the spectrum S of f? For S of f, these two signal Fourier transform is this one and this one respectively. So the convolution of both the two will be representing the spectrum of this S of t. We can represent this signal in unit step function as u of f plus 250 minus u of f minus 250. Similarly, this one also we can represent in unit step function u of f plus 350 minus u of f minus 350. Suppose this part of the signal is x1t and this part of the signal is x2t, then spectrum of x1t is x1 of f and spectrum of x2t is x2 of f. We have already found out x1 of f like this and x2 of f like this. S of f is simply convolution of their individual spectrum, that is spectrum of this one and spectrum of this one will be convolved. So x1 of f convolution with x2 of f. Now one tip to remember, while doing the convolution between two signal, if at least one of them can be represented as in unit step function, then the convolution can be written as minus infinity to f, that is the integration. The unit step function will be derived with respect to frequency and the other signal will be as it is and the convolution will be there. Here, as both the signal are in unit step function, so you can derive either one of them and you can simply represent the convolution like this. Here we have differentiated the x2 of f with respect to tf. So here, as this is a unit function, so its differentiation will be simply impulse function. So here the differentiation of x2 of f is simply del f plus 350 minus del f minus 350, that is in convolution with x1 of f, and the integration is remain as it is. By applying the property of convolution with impulse function, we can simply represent this as x1 of f plus 350 minus x1 of f minus 350. The integration will be from minus infinity to f. The integration is happening in respect of tf. Now this x1 of f we already know. So what will be x1 of f plus 350 and minus x1 of f minus 350? x1 of f plus 350 will be 350 will be added here, and 350 minus 250 will be there. If 350 is added here, then that will become f plus 600. So u of f plus 600 is there, and in the second part it will be simply 100. Okay, so in the second part it will be simply minus u of f plus 100. Similarly, this part also, by putting in place of f minus 350 and in place of f minus 350, we can get this expression. So the total expression will be like this, that will be integrated with respect to df. Now let us represent this unit step function in wave form. It will be looking like this. The waveform will be looking like this, because u of f plus 600 will be up to this point and u of f plus 100 will be up to this point. As it is subtracted, so we will have a square wave and its magnitude is simply 1. So this part is represented like this, and this part also you can represent like this. So this is the waveform, and it will be integrated with respect to f, and the integration will be from minus infinity to f. From minus infinity to minus 600 there is no signal, so the integration will simply happen from minus 600. So if the integration will happen from minus 600 up to this point, the total area under the curve will appear. Area under the curve will be simply 500 into 1. It will be gradually increasing. The area will be gradually increasing up to 100 Hz frequency. Okay, so up to this point it will be gradually increasing. Then as the signal is 0 between minus 100 to 100, the same area will be maintained till 100. So it will be maintained till 100. Next, as this is in negative part, the area will be gradually subtracted, so the curve will be declining gradually, and up to this point, if you see, the area of this rectangle is same as the area of this rectangle. So at this point the total area will be subtracted from this point value, that is the maximum area. So the curve will be gradually decreasing till 600. So this is the integration of this signal. Now this is nothing but the spectrum of S of f, because this expression is simply represented in waveform as this. So this is nothing but S of f, or the spectrum of S of t. Here if you see, the maximum frequency is 600 Hz. So we have the spectrum of S of f, and the maximum frequency is 600 Hz. Then the Nyquist rate is simply 2 times of fm. So the Nyquist rate is 2 times of fm, which will be equal to 1200 Hz, and that is the Nyquist sampling rate of the signal. So option C is matching. Hence option C is the correct answer. Solution to rest of the questions will be discussed in part 2 of this year video. You may click the link mentioned below this video for part 2 solutions. Thanks for watching. Keep watching and keep learning.